Hello, in this recording I'm going to talk about how to combine different types of angular momentum. This is something which happens very often in atoms and molecules. Angular momentum, as we've seen, comes in different types. We have angular momentum due to rotational motion, and we have angular momentum which is intrinsic to a particle, which is called spin. And as we've seen, rotational motion can include orbital angular momentum. For example, for an electron going around a nucleus in a hydrogen atom, and that's described by a quantum number which is called L and takes values 0, 1, 2 and so on. We can have angular momentum due to molecular rotation when we have a molecule which rotates in space, and this can also be quantized and is described by a rotational angular momentum which is usually called capital J, and which also takes values 0, 1, 2 and so on. And then we've seen that the fundamental particles, such as the electron, have intrinsic angular momentum. So in particular, the electron has spin quantum number 1/2. We'll also see that nuclei in the center of atoms can also have spin. This is called nuclear spin, and this may take a range of values depending on the isotope. We denote that spin by the symbol I, and it can have values 0, 1/2, 1, 3/2, 2 and so on, depending on the isotope. So in a typical atom, such as the hydrogen atom, we have a proton which has spin, and then around it goes the electron, which also has spin 1/2. And we also have the angular momentum associated with the orbital motion. So we have the orbital angular momentum, L. So in a hydrogen atom, we have actually three sources of angular momentum: the spin of the proton, the spin of the electron, and the orbital angular momentum. And I want to discuss now about what happens when these angular momenta are combined. There's a very simple rule about how to combine angular momenta. Suppose you have two sources of angular momentum with quantum numbers L1 and L2. So these could be the orbital angular momentum, could be spin, could be two sources of orbital angular momentum. As long as they're angular momentum, the same rule applies. And this is, if you combine the two together, you can generate states which have a new value of total angular momentum called a capital L. And the values of capital L can be as follows. They can be given by the sum of the two angular momenta. They can be the difference between the two angular momenta, neglecting the sign. Or they can be anything in between in steps of 1. So if we take the sum of angular momentum, subtract 1 and keep subtracting 1 until we get down to the difference, these are the possible values for the total angular momentum. Suppose, for example, we have two sources of angular momentum, one with quantum number 2, one with quantum number 5, and combine them together. What can we get for the total angular momentum? So the result is that we can get the sum, which is 7, we can get the difference, neglecting the sign, is 3, or we can get anything in between in steps of 1. So we can also have 4, 5, 6. So we can have 5 different values of total angular momentum. Similarly, if we have two spins, we have one spin 1/2 and we have another spin 1/2. If we add the angular momenta together, we get a 1/2 plus a 1/2, which is 1. And if we subtract the angular momenta, we get 1/2 minus a 1/2, which is 0. In that case, there's nothing in between 0 and 1 in steps of 1, so these are the only two possibilities. So we get a series of possibilities for the total angular momentum, and in atomic and molecular spectroscopy then these possibilities appear with different energies. So let's take an example from the spectroscopy of sodium. So sodium consists of a nucleus with 11 protons and is surrounded by 11 electrons. 10 of them form a shell, and then we have a remaining one which is the 3s electron, and that has an electron spin of 1/2. So the 3s orbital, since it's an s orbital, this indicates that L is 0. But there's also an excited state of that electron in which L would be 1. And if sodium vapor is heated, some of the atoms end up in the excited 3p state and then fall back down to the 3s state, emitting a photon. As we've seen in the previous lecture, the orbital angular momentum, going from L is 1 to L is 0, is released into the photon, which has spin 1. So one gets a spectroscopic line for sodium which is at approximately 589 nanometers. It's yellow light. When spectroscopists looked very carefully at this emission line, they found that there was some fine structure. It was found that there were actually two closely spaced lines, separated by about half a nanometer. And we now understand that this fine structure comes because of a coupling between the orbital angular momentum of the electron, which is L is 1 in the p orbital, and the electron spin due to an effect called spin-orbit coupling. We can use our rules for combining angular momenta to see how this works. So in the excited state of sodium, where the extra electron is in the 3p orbital, then it has L as 1. The electron has spin 1/2, and we can combine these two varieties of angular momenta through spin-orbit coupling to get a total angular momentum, which is usually denoted using the symbol small j, as either 1 plus a half, which is 3/2, or 1 minus a half, which is a half. So there are two states. And indeed these two levels in the split sodium 3p level correspond to these different values of total angular momentum, originating from the coupling of the electron spin and the orbital angular momentum. The two levels with the electron in the 3p orbital are usually denoted by using a subscript to denote the value of j. So the lower level is actually 3p subscript 1/2 and 3p subscript 3/2. So these are split by the spin-orbit coupling. And then we have the 3s state of the sodium electron. This has angular momentum L is 0. So when we couple that to the spin 1/2, we only get one possibility, which is 1/2. So there's no spin-orbit coupling in the 3s state. And the emission of yellow light from sodium is caused by these two transitions. And there's a splitting of about 0.6 nanometers in the spectral line structure of sodium caused by the spin-orbit coupling. Another example is dioxygen, the ordinary molecule of oxygen. Dioxygen is actually a diradical. It has two unpaired electrons. It's a very unusual molecule. But it has two unpaired electrons, and each of those unpaired electrons have spin 1/2. So they can couple together as well. Using the same rules as before, if we have one electron spin 1/2, the second electron spin 1/2, we couple these together and we can get two states. We can get the sum of the two spins, a half plus a half, which is 1, or the difference between the two spins, a half minus a half, which is 0. These are the values for the total spin quantum number, which is denoted by the symbol S. So S is 0 or 1. We saw before that whenever we have an angular momentum quantum number, S for example, then we have 2s plus 1 values of the magnetic quantum number. So for example, for the state S is 1, then we have ms taking values from 1 down to -1 in steps of 1. So that's 3 values. Similarly, if we have big S is 0, then ms can only take the value 0. So that's only one possible value. The S equals 1 state, since there are 3 values of ms, this is called a triplet state. While the S is 0 state, which only has one possible value of ms, this is called singlet state. And the triplet and singlet states of oxygen, they have different energies. So the energy level structure of molecular oxygen, the lowest two levels look like this, with S is 1, the triplet state, and S is 0, the singlet state. And very roughly we can denote these molecular states by denoting the spins of the electrons. For the singlet state, the two electron spins cancel out, so we depict that using 2 arrows, one up and one down. And for the triplet stage, the two spins add up, so we denote that by using 2 arrows in the same direction. And it turns out that the ground state of molecular oxygen is actually the triplet, so with S is 1. But there is an excited state of molecular oxygen which is called singlet oxygen, which is in fact is much more reactive than ordinary triplet oxygen. So that's another example of how spins can combine to generate new states with different values of the angular momentum quantum number. And in fact that process is followed through all the way through nature. So according to latest thinking, it's made up of a variety of different objects. Some are called leptons, which are light particles. And for those of us interested in chemistry or phenomena at ordinary energies, The only one of these we need to worry about is the electron. And as we've seen, the electron has spin 1/2. Now the universe also consists of particles which are called quarks, and it turns out these also have spin 1/2. In addition, there are particles associated with the forces of interaction between the particles. There are many of these, but the one which is encountered most at ordinary energies is the photon, which is the particle of the electromagnetic interaction. And as we've also seen, this has spin 1. Current thinking is that there's also other things in the universe which at the moment are very poorly understood and which go under the name of dark matter and dark energy. So the quarks have spin 1/2, and the quarks combine to make two other important particles. In fact, they combine to make a whole host of many other particles, but the ones which are of most importance for us are called the neutron and the proton. And these are also spin 1/2. So the spins of the neutrons and the proton come from combinations of the spins of the quarks, and also possibly contributions from orbital angular momentum inside the particles themselves. But the upshot of it is that the neutron and proton also have spins 1/2. So in our world of molecules and atoms, we have the electron with spin 1/2, we have the quarks with spin 1/2, which combine together to make the neutron and the proton, which also have spin 1/2, and we have the photon with spin 1. Now the atomic nucleus is composed of neutrons and protons which are bound together, and the spins of the neutron and the proton also combine to make the spin of the nucleus, which is called spin I. And we'll see in a little bit more detail how that works, but basically the neutron and proton spins, because there are many neutrons, many protons in most nuclei, the neutrons and proton spins can either add up or combine or cancel out to make a nucleus which has a different spin. Which spin you have depends on the isotope, the number of neutrons and protons in the nucleus. And then, as we've seen before, the electron can have orbital angular momentum, which can combine with its spin. That's the spin-orbit coupling. And we can also have coupling from the electron to the nucleus. So if we have a typical atom, we have a nucleus with its spin I. We have electrons orbiting around. They have orbital angular momentum L, and we have electron spin. And these sources of angular momentum may couple together. So the electron spin and the orbital angular momentum may couple together. That's called spin-orbit coupling. And as we've seen, this gives rise to phenomena including spectroscopic fine structure. The spin of the electron can also couple together to the spin of the nucleus. That effect is called hyperfine coupling. And it gives rise to even finer spectral structure, which is called hyperfine structure. Now let's look briefly at how the spins of the neutrons and the protons combine to give rise to the spin of the nucleus. So let's take, for example, a simple nucleus such as one which contains one neutron and one proton. So this is actually a nucleus of deuterium. It's an isotope of hydrogen, since it only has one proton. But it has a mass number of 2, meaning that the total number of neutrons and protons is 2, so that as well as the proton there must be one neutron. So that's called deuterium. Now we've seen that both the neutron and the proton have spin 1/2. So again, we can combine the neutron spin with the proton spin, and we can deduce that there are two possibilities. The spins can add up and we get spin 1, or they can cancel out and we get spin 0. We have two nuclear levels, one with spin 1 and one with spin 0. And it turns out for deuterium that spin 1, so the nuclear spin quantum number I equals 1, is lower in energy than the nuclear quantum number I is 0. It's not easy to decide the order of these energy levels. The coupling rules for angular momentum tell you that there are two levels with I is 0 and I is 1, but they don't tell you about the relative energies, which one is the ground state. That's something which nuclear physicists make theories about and can predict. But I'm going to treat that simply as an empirical fact. So for deuterium there are two nuclear energy levels, but since we're talking about nuclei here, the energies between these levels are extremely high. And in ordinary circumstances, when we're not talking about radioactivity or nuclear physics, we only need to worry about the nuclear ground state, which has spin 1 for deuterium. So we say that the deuterium nucleus has I equals 1. And the same goes for all the other isotopes in the periodic table. A nucleus of carbon is defined as one with 6 protons. And since the mass number is 12, we have 6 neutrons as well. Proton has spin half, the neutron has spin half, and those spins can combine in very many different ways. So again, we get a set of nuclear energy levels with different values of the nuclear spin. But it turns out for carbon, the nuclear ground state has spin 0. So the nucleus of carbon-12 does not have nuclear spin, and that's actually quite unusual in the periodic table. Most nuclei in the periodic table do have spin. So this diagram here shows, for example, the nuclei which have spin half in their nuclear ground state. You can see that most of the elements in the periodic table don't have a spin half ground state nucleus. The ones which do are very important for NMR spectroscopy. So this includes the proton, the nucleus of ordinary hydrogen. Single proton has spin 1/2, so that's the nucleus of hydrogen 1. That's the most common isotope of hydrogen. Similarly, the ground state of the most common isotope of fluorine, which is fluorine 19, also has spin 1/2. And the most common isotope of the element phosphorus, that also has spin 1/2. Other important nuclei with spin 1/2 are carbon-13 and nitrogen-15. These are rare isotopes of these important elements. This shows the incidence of nuclei with integer spin in the ground state, and in fact there are very few of them. There's deuterium, as we just discussed, which has nuclear spin 1 in the ground state. Another important one is nitrogen-14, which also has nuclear spin 1 in the ground state. In fact, most of the nuclei in the periodic table have half integer spin. That means 3/2, 5/2, 7/2, or 9/2. As you can see, these are distributed widely across the periodic table. Some important ones are sodium-23, which has nuclear spin 3/2 in the ground state, and aluminium-27, which has nuclear spin 5/2 in the ground state. So let me describe now one case where the nuclear spin is important in spectroscopy. Let's consider an atom of cesium. The most common isotope of cesium is actually cesium-133, and this turns out to have nuclear spin 7/2 in the nuclear ground state. Let's now consider the interaction between the cesium-133 nucleus with its spin 7/2 and the valence electron of cesium. Let's suppose that that valence electron is in the 6s orbital. So that means it has angular momentum quantum number L is 0. So there's no orbital angular momentum, so we only have to worry about the coupling between the electron spin, which is 1/2, and the nucleus, which in its ground state has spin 7/2. And we can use the usual coupling arguments to deduce what are the states which result from this coupling. So we end up with a 1/2 plus 7/2, which is 4, and a 1/2 minus 7/2, ignore the sign, which is 3. And this coupled quantum number is usually by convention denoted F. So the energy levels of a cesium atom in its electronic ground state, so with orbital angular momentum 0, is split into 2 levels, with the total quantum number F being 3 and F being 4. And this splitting is due to the interaction between the nucleus of cesium and the electron spin. So this is called a hyperfine splitting. And that splitting frequency is very well defined, in fact. It's given in frequency units by 9.129631770 gigahertz. In fact, it's given exactly by that number. This hyperfine splitting is basis of the cesium atomic clock, and in fact the second, the unit of time, is defined as 9.129631770 times 10 to the 9 periods of the cesium atomic clock. Okay, we've seen how different types of angular momenta combine together and how that combination leads rise to the structure of our universe. How the spins of the quarks couple together to make the spins of the neutron and the proton. How the neutron and proton spins can combine together to make nuclear spin. How electron spin can couple to the electron orbital angular momentum through the effect called spin-orbit coupling to give rise to spectroscopic fine structure. And how the spin of the nucleus can couple to the spin of the electron through the effect called hyperfine coupling, an effect which is used for the atomic clock. In the next lecture I'll discuss the dynamics of spins in magnetic fields, which is the basis of magnetic resonance.